Good morning. Yes, good morning, good afternoon, good evening, wherever you are, everybody. It gives me the pleasure and honor to welcome you all in the webinar of climate change impacts on surface and groundwater resources. This webinar is organized jointly between the African Regional Working Group of the International Commission on Irrigation and Drainage and United Nations Economic and Social Commission for Western Asia, ESCWA, and the Arab Center Organization for Studies of Arid Zones and Dry Lands, ACSAD. In this regard, I would like to thank ICID President Dr. Ragab and the ICID main office, Dr. Carol Shoshani, Director of Arab Center for Climate Change Policies Cluster, Leader for Climate Change and Natural Resources Sustainability at UN ESCWA. And last but not least, for Dr. Ziad Khayat, Economic Affairs Officer at UN ESCWA, for their great effort and support for the preparation of this webinar and for supporting the activities of African Young Professional Forum. No doubt that climate change will affect water resources through its impacts on the quantity, variability, timing, form, and intensity of precipitation. Climate change is already affecting water access for people around the world, causing more severe droughts and floods. Climate change impacts the water cycle by influencing when, where, and how much precipitation falls. It also leads to more severe weather events over time, increasing global temperatures, causes water to evaporate in large amounts, which will lead to higher levels of atmospheric water vapor and more frequent, heavy and intense rains in the coming years. Agriculture is the largest consumer of water. Growing demand necessitates integrated management and planning to avoid over-exploitation and eventual depletion. However, data and understanding are lacking at a regional level. This webinar will focus on climate projection in Africa, the region, and UK, and their impacts upon selected aquifers and surface water. Such case studies can bridge climate science towards integrated management. We are looking forward to hear and learn more from 5 international experts, and I wish you all a very rich and fruitful webinar and valuable discussions. My pleasure and honor to introduce Dr. Ziad Khayat, who is going to be the moderator for the webinar. Dr. Ziad, he is the Economic Affairs Officer, Water Resources Section, Climate Change and Natural Resources Sustainability Cluster, United Nations Economic and Social Commission for Western Asia, ESCWA. Dr. Ziad, the floor is yours, please.
Thank you very much, Dr. Muhammad, for that introduction. And indeed, this webinar is in the spirit of continued cooperation between ESCWA, ICID, and the African Young Water Professionals Forum. We've been coordinating and cooperating on activities for the past few years, and we hope that has been beneficial to all of us and to the youth group that has been taking part in these activities. I won't take too long, then I'll turn over to our keynote speaker, Dr. Ragab Ragab, President of ICID and fellow principal hydrologist and water resources management specialist at UK Center for Hydrology. Dr. Ragab will be speaking about the impact of future climate change on surface and groundwater resources with some key examples from the UK. Dr. Ragab, please.
Thank you very much, Dr. Wahba and Dr. Ziad for inviting me. And it's really good to see the cooperation between ESCWA and ICID. So thank you really for inviting me for presenting some work that we did in the UK. I will share the screen now and
Excellent. We see it, Dr. Ragab. You can start.
Okay, thank you. Yeah, really the impact of climate change, especially when temperature is increasing, it will have effect in the food, especially in many areas, developing regions as well. At the same time, the water is expected in the Mediterranean area in particular to significantly decrease in terms of availability. And at the same time, also, we expect to have more extreme weather events, that's from droughts and flooding. And really, it's really a history telling us that there is climate change and this is really happening. And in the UK history, I can really show you here how many drought events since the recording in the UK started before 1800. And it has been really so many drought events, and a lot of people inside UK and outside UK, they think the UK is a water-rich country and we cannot be subjected to drought. But the drought is really getting more frequent in the past years, and also the drought has a regional impact, while flood has a local impact in communities. And for that reason, the government here in the UK, they started to fund research in droughts only in the last years, because drought was not seen as a threat by the climate change. So there are some information about the history of the drought, and also it has been really felt here in 2003 and the later 2006, 2012, 2018, and the last really couple of decades, it has been repeated, and some reservoirs really went dry. And then we managed to get awarded a project by the government to look at the drought from Scotland in the north all the way down to Fowey in Cornwall. So we have really a gradient of rainfall, high in the north and low in the south. So we managed to select 7 catchments, and from north to south and from east to west, they differ in rainfall and temperature gradient. And we used a model. It has been developed under EU-funded project MEDIS, and that model is called IHMS, Integrated Hydrological Modeling System. It is a 3 models, DICASM, which is a catchment scale model for the unsaturated zone, and that sits on the top of ModFlow, which is groundwater model, and through interface, and also it links to a seawater intrusion model. So they are really 3 models linked to each other. And this is the acknowledgement for the grant, and also I would like to acknowledge my team members. And we have been working with the stakeholders in those 7 catchments and authorities. And the framework that we did for the modeling is that we are using data from 1961 to 2012. And we have been looking to identify the drought using several indices, SPI, that's standardized precipitation index, and SPI, which means that the same, but including evapotranspiration, and the Reconnaissance Drought Index, so moisture deficit and wetness index as indicators for the drought. And we have been looking at the scenarios of the UK CP09, and these scenarios, they come in 2 forms. The first form is the joint probability that gives you percentage decrease or increase in rainfall, or the increase or decrease in temperature. But also you have the weather generator that gives you a daily values for possible change in temperature, rainfall, radiation, vapor pressure. And we look at the impact using these 2 sets of scenarios, joint probability or weather generator data, to look at the drought risk and potential actual evapotranspiration, groundwater recharge, and the stream flow. And also we added the land use impact using different realistic scenarios. And for the model data we need the rainfall, land cover, soil series, elevation, land cover properties, soil properties, and data on abstraction, irrigation, wastewater discharge to rivers and water bodies. And this is one example of the 7 catchments, that Don catchment and Sheffield area, Midlands, in the middle of the UK. And the catchment is 373 kilometers square, has got 23 reservoirs. And we looked at the land cover map to see what the land use is. And most actually, if the land use is grassland, with only 6% arable land. And we divide the catchment into squares. Each square here is 1 kilometer grid square. And we have got 435 grid squares covering the whole catchment. Then we run, of course, the catchment using the catchment scale model from unsaturated zone first. Then we calibrate the model against the stream flow, and this is a couple of years to calibrate the model. And as you see here, the model calibration was successful with matching factor, Nash-Sutcliffe criteria, or efficiency factor of almost 92. And then we validate the model with another set of data using the same parameters. And this is example of 10 years validation using the same parameters obtained from the calibration. And then we started to look at what are the indicators here. We are working with stakeholders and meteorologists. They have their own drought indices. The hydrologists, they have their own drought indices. The fishermen community, they have their own indices, and agriculture community also, they have their own indices. So for deficit, when we have a deficit precipitation, of course, the standardized precipitation index is important for the meteorologist as indicator for the drought. And when you have evapotranspiration high, you create soil moisture deficit and also create a low wetness index values. And that would affect the flow to the groundwater recharge. And here you have the meteorological droughts as SPEI and the Reconnaissance drought indices that also might be considered as meteorological. And you have the hydrological agricultural drought indices like soil moisture deficit and wetness index, but it is also agricultural drought index like SMD and wetness index would be also useful to have. And here you have these indices. Here, example of the standardized precipitation index without evapotranspiration included. And you have also the SPEI, where evapotranspiration is included. And here you can see that the two indices, they are more or less reflecting what happened from 61 to 2012. We have in 1976, the well-known drought here in the UK and in Europe in general. And also we had here in the 1996 also another drought. And you can see here the drought started to be more frequent as we went on from the 70s until now. And this is the way we calculate the drought index or Reconnaissance drought index. It is a ratio between precipitation and potential evapotranspiration. However, we actually developed another way to calculate it based on the net precipitation and the actual evapotranspiration rather than the potential. And you can see here that this is the Reconnaissance drought index from 62 to 2012. And you can see here in 1976, the RDI was really quite low, below zero. And also in 1997 or 96, that also it went down quite far. So these are the periods where the UK were subjected to drought. And this is really the indicator that can explain the periods and how far we were from the drought. Another important index for agriculture in particular and irrigation in general is the soil moisture deficit, on which we base our crop water requirements. And here you can see the 1976 famous drought here, where the wetness index, which is scaled soil moisture or the soil moisture deficit, both of them, they show that the soil moisture deficit was high, closer to 140 millimeter, which means that there was a need to irrigate agriculture, which is mostly rain-fed. And the wetness index is actually scaled soil moisture. And that's the scaling of soil moisture is better because of spatial variability between different locations, and model grid squares and topography and so many variations can be all integrated into one index that can explain the degree of wetness or degree of drought. And here, using that wetness index with the scaled soil moisture, we can also identify the period where the catchment in 1975-76 and also in the late 1900s, 1997, that the big droughts here can be identified using that indicator. And also you can have from the model the spatial distribution per grid square, and you can see here a dry year like 1976 versus an average rainfall year, and you can see here that the actual evaporation an average year for the same date, 10th of August, was can go up to 7, while in a dry year like 76 hardly exceeded 1.5 millimeter. And also you can look at the wetness index of the root zone and also in a special format, and you can see the difference between a dry year of 1976 versus average year 2008, which you can see here. 2008, the soil had more water. We use the joint probability plot, which provides percentage change and future precipitation and plus or minus change in temperature. And we can use that for seasonal and monthly changes. And also we use the weather generator, which provides a daily predictions of precipitation, temperature, sunshine hours, and relative humidity. And we used 3 periods from 2010 to 2039 and 2040, 69, 2070, 2099. Those are 3 periods we used, and our baseline data was 1961 to 1990. And this is the models that predicted the future climate change coming from the Hadley Center. And the joint probability here, it gives you an idea about possible change in temperature versus precipitation. And the probability actually increases as you go to the center. And then you can look for the value of a change in precipitation for a certain value of temperature. And it is coming from grid square of 25 kilometers by 25 kilometers. And we actually, for the weather generator data that comes on a daily, as a daily values, we use 100 realization to generate the scenarios and to also tackle the uncertainty associated with these scenarios. It's because the weather generators gives us data based on the baseline of the whole UK. We need to adjust that to the catchment baseline. So for that, we have to do a bias corrections to avoid that our baseline data is affected by a different baseline of the UK in a whole. And this is what we get. For example, this is for low emission and high emission, medium emission scenarios. And you can see here the change in temperature, especially in summer, might go up to 308 in the period of the 80s. And also you can see the change in precipitation here for the different scenario periods that we might get even a less water here, especially in summer where irrigation is needed most. And we run the model with these scenarios for the 3 periods. And this is the results we get for the stream flow or the river flow. And you can see here that the river flow is decreasing in most of the seasons. There is some small decrease in winter time, but most of the time here and in the other seasons that we have a decrease in river flows. And in terms of groundwater recharge, you can see here in all scenarios and all emission levels that we have a low recharge rate to the groundwater, and that recharge is increasing with time from the 20s to the 80s. And also you can see that in summer in particular, the recharge is the lowest with time. And we also looked at the soil moisture deficit, And you can see here the soil moisture deficit is increasing with time and also increasing with the emission level. The same actually with the potential evapotranspiration. The wetness index, the soil gets drier and drier, especially at higher emission and in summer in the late 80s, more than the 20s. And also actual evaporation, you can see the actual evaporation is increasing with the level of emission and also during the summer higher than, of course, the winter. And we looked at the possible drought events in the future, and we can see here there is indication that in the future we are going to have more frequent drought event, and the severity of the drought events will increase with the emission scenario and also with time. You can compare here with the baseline data compared to what we are expecting by end of the century in terms of the number of the drought event and also the severity. And we compared what the data we use from weather generator, which is daily data, compared to the Joule probability method, which actually is just a probability of a change in temperature and rainfall. And we can see here that in terms of river flow, they are similar, but the Joule probability gives you more reduction than the weather generator. And also the actual evaporation here, they are quite similar, the two sets of data we used. And also here, the same for soil moisture and the groundwater. Groundwater recharge might be reduced more when we use Joule probability. So the UK CP09 projected more rain in winter and reduced the rain in summer. However, the increase in winter rain did not produce similar increase in stream flow or groundwater recharge. Modeling results indicated a decrease in summer river flows, groundwater recharge with time and with increasing emission level. The severity and the frequency of the drought events will significantly increase with time and the emission level in all catchments, on the 7 catchments, what I meant here. All the applied drought indices, soil moisture deficit, wetness index, and Reconnaissance drought index identified an increase in the severity of the drought with time and was increasing the emission level. Increasing in terms of the land use, we found that increasing broadleaf woodland area reduced the river flow and groundwater recharge, but increased the evapotranspiration. Increasing heather or grass or crops areas by replacing trees would increase river flows, groundwater recharge, and reduce evapotranspiration. However, the impact of climate change was greater than the impact of land use change on water resources. We tried to look at uncertainty level of our results because all the funders, they like to have uncertainty level associated with the results. We applied generalized likelihood uncertainty estimation group, indicated that the model captures above 70% of the observed river flow, what they call it containment ratio, CR, which means that more than 70% of the observed flow values are included in the 5 to 95 likelihood weighted quantiles envelope. This gives confidence in the model of the stream flow. And I can show you here how we calculated the uncertainty levels. This is the results of, we can do that daily and monthly and annually. And here you can see the top figure here. The solid line is the observed river flow data. And what you see here in the shaded areas are the model predictions between the 5 and 59 likelihood weighted quantiles. This area is validation and this area coming from the calibration. So this is the monthly values and here's the annual values. And you can see here you have less noise in the data because you aggregate the monthly values. So you have less noise, have more smooth curves. The containment ratio, when we run uncertainty for monthly flows, is about 76 because of course you have more variations when it comes to monthly data. And when you calculate the flows aggregated to annual values, then you have less uncertainty with containment ratio 85%. And also you have another way of plotting the uncertainty levels. And this is here, shows you the red line is observed values. And this is the prediction limits or bounds or envelope of the model. We looked at the possible water demand by talking to the councils, how many houses are going to build, if there is any change in the land use, and what will be the water needed for the new housing. And we estimated the water demand in the future until the end of the century against the possible water availability until that time. And you can see here, there is a gap in between the water demand and supply, and that gap is actually widening with time. And we found that in the 7 catchment, apart from the Scottish catchment. And these are publications that you can look up for details, but in all the 7 catchments, apart from Eden in Scotland, there was a gap between the future water supply and future water demand, and that gap is widening over time up to 2099 if water demand is not sustainably managed and controlled. So the uncertainty in the climate actually predictions arise from our imperfect knowledge of future rates of human-made emissions and how this will change the atmospheric concentration of greenhouse gases. The second is the response of the climate to these changed conditions. Also, the uncertainty in the results could be attributed to the model assumptions, processes descriptions, mechanisms, mathematical formulation, and numerical schemes. In nature, all processes operate simultaneously, while in the model, they don't. They follow order of execution based on flow chart. If evaporation comes after infiltration, expect recharge, soil moisture to be different from the other way around. Linearity exists in model processes, but not in nature, where nothing is linear. Measurements, stream flow, soil moisture, groundwater level, and parameter values, soil physics, plant parameters, and so on, they have also uncertain level and accuracy. The mismatch between the scale of the model, which is 1 kilometer grid square, compared to the observation, which is a point scale, can also give you a contribution to uncertainty. The assumptions in climate change scenarios and predictions can also contribute to the uncertainty in the results. In any case, no one trusts the model except the man who wrote it. Everyone trusts an observation except the man who made it. In modeling a complex system, it is better to be approximately right than precisely wrong. And thank you.
Thank you. Thank you very much, Dr. Ragab, on this comprehensive presentation, and which you've used climate data and several indexes to look at the climate change effects in the UK. And it's quite interesting to see that, as you said, our perception that the UK is a water-rich country, but you have shown through these analysis and the indexes that there is a gap between demand and supply, and that will be more and more affected by the climate change. We thank you for this presentation. It's very useful. We will take another presentation, then we can, you're able to stay with us, Dr. Ragab, yes, to take a few questions after the next presentation?
Ziad?
Dr. Ragab?
Yeah, I'm available. Yeah.
You're available, excellent. So we'll have one more presentation, and then we'll move to you. Yes.
Yeah. Sorry to interrupt, but can we change the order a little bit, because as I mentioned before, in a meeting, I just get out of the meeting, or if it will be difficult, it's okay. But if it is possible,
is it possible to have, because of the natural flow of the presentation, we'll have Dr. Marlene, then you can follow after it. Is that okay?
Okay.
So I'll turn now to Dr. Marlene Tomaskovich, who's the climate change and geospatial analyst expert at the Arab Center for Climate Change Policies, Climate Change and Natural Resource Sustainability Cluster at ESCWA. And she will provide an overview of climate change impacts on water resources in Africa and the region. Marlene?
Thank you, Ziad. Good afternoon, good morning, everybody. I will give a brief introduction about what we can expect in terms of climate change for our region. I'm talking specifically about Africa and the Arab region. And first, I'd like to, wait a minute here. What's the wrong one? Hold on a second here. So first, I want to talk about what we found from the latest IPCC report. This report is the assessment report number 6. And part of the assessment report divided the globe into different regions, as you can see here. And we'll take a closer look at the regions in our area of interest. For example, in the Mediterranean region, which includes Northern Africa, as well as Lebanon, Jordan, parts of Syria, and Palestine, we can expect projected decreases in mean precipitation, increases in fire weather conditions, decreases in mean wind speed, and observed and projected increases in drought. Similarly, in the Sahara, we can expect projected increases in heavy precipitation and pluvial flooding. Here in Western Africa, we can expect observed, we have seen observed increases in river flooding, and counter that, we've seen observed increases in drying and droughts. We can expect projected increases in mean wind speed and continued increases in both heavy precipitation as well as pluvial flooding. Thirdly, in Central Africa, we could expect observed decreases in mean precipitation. We've experienced decreases in SPI. SPI is a standardized precipitation index that Dr. Ragab was referring to. In counter, we could expect observed increases in droughts, but then we could expect projected increases in precipitation as well as flooding, both in pluvial flooding and in riverine flooding. Here in the Horn of Africa and Northern Eastern Africa, we have seen an observed decrease in precipitation and observed changes in terms of slow and glacial amount. There is a projected increase in precipitation, but also projected decrease in drought. And then in Southern Eastern Africa, projected increases in flooding, projected decreases in snow, increased intensity in terms of tropical cyclones, and combined with that are wind speeds, precipitation, and intensity. Here in Western Southern Africa, we have seen observed decreases in precipitation, but also observed increases in heavy precipitation and pluvial flooding, as well as drought. And this is expected to be exacerbated with a greater warming of 1.5 degrees Celsius and above, and projected increases in wind speed and fire conditions. In Eastern Southern Africa, we have seen observed decreases in precipitation, but also observed increases as well as projected increases in precipitation, as well as flooding, increased drought, increased fire weather conditions, and increased tropical cyclone wind speeds and associated precipitation. And lastly, in Madagascar, we've seen some observed increases in precipitation, projected increases in drought, projected increases in flooding with precipitation, as well as projected increases in tropical weather. And lastly, both in Western Central Asia, as well as the Arabian Peninsula, we have seen an observed increase in drought frequency in the last few decades, as well as an observed increase in extreme precipitation, primarily in elevated areas, mountainous areas. There has been mountain permafrost degradation at high altitudes, which has increased the instability of mountain slopes, an overall decrease in snow cover, but a projected increase in precipitation volume, intensity, and frequency, combined with increased spatio-temporal variability in precipitation, and an overall decrease in precipitation during the summer with increase during winter. So we've seen kind of a common theme across both Africa as well as Western Asia. Climate change impacts are expected to significantly impact surface and groundwater resources driven by precipitation due to these both extremes, drought as well as flooding. So how can we adapt to this? We, as water resources engineers and managers, irrigation specialists, we can use hydrological models like Dr. Ragab was showing to help project these impacts and provide these impacts and results to policymakers and planners. We can do this in two ways. We can use trend analysis based on observed data, or which is our preferred method, which we'll show you in a minute, is analysis using climate modeling outputs. So again, with these methods, trend analysis, it's simple, we're familiar, we use observed data. It's a comfortable, common approach. But however, it's based on the past. We know the world is changing. So it's better to use climate modeling outputs from our perspective, which considers this changing climate. But however, it's unfamiliar to a lot of us. There's some challenges, but hopefully today we will kind of overcome some of those challenges using climate data, and you'll feel much more comfortable using this approach. So how do we project the future climate? The last Ipcc report, AR5, which was based on CMIP5 models, which are the previous generation models, but still very valid today, use what we call representative concentration pathways, or RCPs. And these RCPs consider different greenhouse gas concentration trajectories, which is not necessarily emissions. It's more than emissions, as we're talking about CO2 gases as well as other atmospheric gases that can impact the climate overall. And you can see as of 2015, and the trend is actually continuing till today, we're kind of following this higher end path. The most current paradigm to project future climate incorporates both of these RCPs with these shared socioeconomic pathways, or SSPs. And this considered those aforementioned greenhouse gas trajectories with different climate policy scenarios. And they range from SSP1, which is a very sustainable climate. We're doing wonderful in terms of adaptation as a globe. We're doing wonderful in terms of mitigation as a globe, all the way up to SSP5, which considers a fossil fuel development, rapid economy growth and unconstrained growth. So it's kind of a different range to consider. And we're kind of following along the same path, kind of leaning toward SSP 8.55. So we're kind of going to wind up in this range as our current trajectory. So what does this mean for our region? I'm looking here at projected changes in temperature for the near term, which of course is 2021 to 2040, which of course we're in that period at present. We look at it over a 20-year period because I'm sure you've seen through your observations, temperature doesn't follow a linear path. I mean, there's some years that may be a little higher in temperature, some that may be a little lower. You may have heard sometimes in the news during a cold snap during the winter that people are skeptical about climate change. Okay, these little nuances in weather do occur, but weather is weather. It's daily observations, it's daily changes. Climate assesses changes over a period of time. So we're looking at a 20-year period. So if you look at these values, I see two different columns. Here are the projected changes in temperature compared to the pre-industrial period. And the second column is compared to the recent past. This period has been defined by the Ipcc in the latest report for the baseline period. And you see three values. So here again is that sustainable low emission scenario, the low greenhouse gas concentration scenario, all the way up until that fossil fuel development, higher greenhouse gas concentration scenarios. This is, formerly a lot of people referred to this RCP 8.5, SSP 8.5 as kind of high emissions. But the truth be told, this is baseline. This is kind of no or minimal global policy. It's again our current trend. The IPCC thinks we may be heading toward this SSP 3 7.0 as a more realistic scenario. So that's why I included those values here in the middle. You can see not much changes, between the values for the near term, because of course we are currently in the near term. But you can see compared to the global mean, particularly in Northern Africa and in Western Asia, you can see we're exceeding those values compared to the globe. Here are the same values for the midterm, which is in the very, very near future from 2021 to 2060. And you can see particularly here in the Arab region here, you can see values greatly exceeding the global mean. So, and there's also some exceedances here in Southern Africa as well. So overall, most of the region is warming at a faster rate than the globe overall. So global climate model, how do models work? So we have these global climate models which simulate the climate based on well-established physical principles. There are several different research agencies around the world who develop global climate models, and they've been well established and they're used by the IPCC as well as other institutions to be used to assess climate. They have demonstrated the ability to reproduce the observed recent past, so they can be compared to assess changes in the past and assess them compared to what we could expect in the future. But however, these global climate models or general circulation models are limited to simulate certain regional features, particularly when it comes to precipitation, tropical weather, ecosystems. So for those, we go to what are called regional climate models. And these regional climate models are nested within these global climate models, but they simulate the climate based on regional specifications. They consider much more regional topography, much more regional boundary conditions. And these regional climate models are at a much smaller spatial and temporal scale. The last set of models for CMIP5, they vary, but generally about 50 kilometers. And the more recent data sets for CMIP6 are even finer scale at 10 kilometers. With bias correction, what we do is kind of assess these although global climate, these regional climate models are very, very good. Sometimes, particularly when we're analyzing for hydrology, there is still a little bit of bias within these models and a little bit of differences. So what we do is incorporate observed data into the models to improve their outputs. But bias correction is not needed for all studies. It's recommended again for hydrological studies, for impact studies, but for many other climate applications, it's certainly valid to use the raw climate modeling outputs. To do bias correction properly, you need a long-term period of data, observed data, which generally is recommended to be about 30 years. And to do bias correction properly, you also should do bias correction for the entire climate domain. So we have data for the Arab region, and bias correction was done across the entire region simultaneously. You should not correct necessarily just for a particular subregion. So where can we get these climate modeling outputs? There are different sources. One is Cordex, and we have a document available on our website, RICCAR.org, that you can refer to offer guidance to obtain these Cordex modeling outputs. Or you can obtain data for the Arab region from our website, which is bias corrected data that is utilized for our region. So either source is very valid. So what are we talking about with Cordex and RICCAR exactly? So there are many, many different domains that are of interest to our region. There is a European domain. Again, there's the Arab domain or RICCAR domain, or MENA, Middle East, North Africa. There's also Region 5 for Cortex, which includes the entire continent of Africa and beyond. And then we have the most recent data sets we've developed as part of RICCAR, which is the MESREC domain. The Cortex domains currently are available solely for CMIP5 models, the RCPs. Updates for CMIP6, the SSPs, are currently in progress. They're just not available for download as of yet. But our MESREC domain data sets are based on CMIP6, so they're definitely latest generation models. So why may you be interested in the European domain? First of all, these data sets are available at a small scale of approximately 12.5 kilometers, as well as a little bit larger. They have both raw and bias corrected outputs, which is suitable for hydrological studies. Three different scenarios from the lower greenhouse gas concentrations to the higher or baseline conditions. Many, many different models, and I'll explain why this is important shortly, as well as many different regional climate models. So you can have different combinations for your use. For the African domain, I apologize, but they're only as raw RCM outputs, and that's okay. I mean, there's no bias corrected data available, but for many purposes, the raw outputs are more than sufficient. And again, several different models to select from for use. The Arab domain, there are both raw data outputs, which are available on the Cortex ESGF site, which I showed earlier, as well as bias corrected outputs available from the RICCAR website. We have limited data for RCP 2.6, but we have substantial data for both RCP 4.5 and RCP 8.5. My colleague, who will be discussing about groundwater analysis in Morocco, used bias corrected data from this domain to assess climate impacts upon groundwater aquifer in Morocco. And then again, our most recent data sets, the two following presentations on Palestine and in Iraq used these data sets, the MESREC domain, which are available at 10-kilometer resolution. They're available for both raw and bias corrected data using this baseline scenario of SSP 5, 8.5, 6 different models, and downscaled using 1 RCM. So you saw there are many, many models, and these models are selected based on timeframes of the project, resources provided, the availability of boundary forcing data, their spatial resolution, and they are designed to have a representative spread about climate sensitivity. There are other agencies who do climate models, but not all of them are applicable to a given domain. So some frequently asked questions. So which model should I use for my area study? I'm asked this a lot because there are many, many models, and we are busy people. We like to do the most minimal amount of work we can to basically get the answer we need. However, it is recommended to use several modeling outputs. At least 3 is a given minimum. More is definitely better, but they have to be of the same spatial resolution and of the same climate scenario. It used to be recommended that they be from the same domain, but that is not necessarily the case. Current practice is to actually do cross domains, but you still need to have the same spatial resolution as well as the same climate scenario. You can't mix and match, otherwise the results will be invalid. Can I do my own bias correction? It's not recommended. Again, it reduces systemic errors in the models, but requires a detailed methodology and long-range data across the Arab domain. Even though I'm a climate specialist here at ESCWA, I actually do not do bias correction myself. I defer to our modeling experts in Sweden to do this. We have daily climate data. The input data is daily, and how should I present my results? Well, because models, of course, they have uncertainties. We talked about uncertainties in the previous presentation, and models are not perfect. Even climate models are not perfect. So it's recommended to present the results as an ensemble. And what an ensemble is the mean result over a 20-year or even a 30-year period. We generally use a 20-year period from all models and present the results. So for example, the next three presentations will talk about the groundwater results, and they'll present data over different 20-year periods. However, because of nuances, because of sensitivities in both surface and groundwater models, it is acceptable to also present a time series analysis from each climate model to show this variability. How do I extract climate data? Well, it's available in what we usually call a Netcdf format. Some data sets are also in a GRIB format, but it's much more common to have climate data in Netcdf, which kind of compresses the data sets and are available for use. There are different methods you can use to extract Netcdf data, either it be daily or monthly, what have you. One method is using GIS, either using QGIS or ArcGIS. And a couple of years ago, we did a on-demand webinar series. You can find the link here. You can refer to that to see how to use Netcdf climate data sets in GIS. And we have a training manual, which you see here, available from our website. And next month, the end of next month, I am targeting a webinar using a software called Climate Data Operators, or CDO, which is a faster approach to extract climate data sets and as well as process the climate data sets. Another question is, can I use observed data with climate modeling outputs? Which is a common thing. A lot of people want to use observed data, particularly to model the historical period, and then compare to the future using the climate modeling outputs. But however, you're comparing two different things using that approach. There will be different methodologies, and you won't be able to tell whether the differences are attributed to climate change or differences are attributed to your climate modeling inputs, your climate inputs. But you can use observed data to calibrate your model. So you would calibrate your model first, and then you can run the model with climate modeling outputs as your input. So with that, that's it in a brief. The next three presentations will kind of go into more applications, and thank you for listening.
Thank you, Maureen, for that comprehensive overview. I think, as you mentioned, we've done several training, and several of the topics that you've done could actually take a day or two to fully explain. But that was an excellent overview, and there's a lot of wealth in that presentation. We will share the presentations with Dr. Muhammad Wahaba, who will be able to circulate it around for those that want the presentation. I think there was a question on that. There's a question in the Q&A, and I'll ask that. And if any of participants have questions, they can either raise their hand or type them in the chat box. I think Dr. Ragab answered a question on the link to the models, and that's available on the ICID website, as you said, Dr. Ragab.
Yeah, under models and tools.
Under models and tools, excellent. There's a question saying, is there any criteria which needs to be considered when choosing a baseline period for climate change analysis studies?
We assessed the baseline period based on the latest Ipcc report. They compared to the period in 1995 to 2014. The reason for that is because the historical models run through 2014 for CMIP6. So it's not an arbitrary period that they pull out of the sky. But we kind of follow that same approach to use that same period. But you can certainly compare to other periods if you want to go to further in the past, or you know, for example, pre-industrial periods or later. I mean, Dr. Ragab used 1961 to 1990. That's a perfectly valid comparison period. So it is up to you and the purpose of your study.
Dr. Ragab, you'd like to add anything on that?
Yes, I think I agree very much really with Marlene that it depends on data availability. And I had two postdoc from Brazil, and they hadn't really that long period of the UK, 61 to 1990. So they used their own data. I also got a PhD from Italy, who also used a shorter even period because they didn't really go as far as 30 years of data. So it is really meant as a baseline to compare the relative change too. So that's really the benefit of having a baseline.
Okay, thank you. There's a question in the chat which is saying, what is the resolution of CMIP6 for ASHR AP for East Africa, and what about the other scenarios data other than 8.5, example 2.6, 4.5? Marlene, you'd like to take that?
Yes, thank you. For East Africa, for CMIP6 models, they are not available online yet, and I'm not privy to that information. My only guess is it will be approximately the 10-kilometer resolution. That's kind of the trend for CMIP6. So hopefully those will be available shortly. Again, we focused on SSP 5, 8.5 because that is currently baseline, is currently considered no policy, no global, no strong mitigation policy, no strong adaptation policies. So, but the other scenarios are definitely of interest to researchers. For the MESREC domain, we will have a second scenario coming out next year for 2023. To satisfy the need of researchers to have a wider range of results. But as for East Africa, the scenarios that will be modeled for CMIP6, again, I'm not privy to that information, but they generally, to meet the Cordex demand, will definitely have both the current guidelines for Cordex will have both SSP 5, 8.5, as well as SSP 1, 2.6. They'll have a minimum of 2 scenarios, and then maybe more from there, depending on funding availability and the modeling agencies. So, but we'll have to keep an eye out for that. I certainly will share that information once I know.
Okay, thanks. I see a hand raised in the chat. So if Godwin Adizil Akulia could unmute and ask the question. Godwin?
Yes, sir. Thank you very much for giving me the opportunity. My name is from Ghana. The first question goes to Dr. Ragab. I was having a bit of a network. Hello?
Yes,
can you hear
go
me?
ahead. Yes, go ahead.
Hello, can you hear me? Hello?
Yes, we hear you, Godwin.
Hello? Okay, all right. Yeah, goes to Dr. Ragab. Actually, I was having a little bit of a network challenge, but when he was presenting the result conclusions from the modeling process, there was a statement he made that I want him to maybe throw more light on. That change was greater than the impact of land use. Maybe I didn't get the extra light on why is that. What accounted for that? The fact that the impact of climate change was greater than the impact of land use change in the modeling. Then the other question is for the second speaker. When she said that we can get some of the data, the climate data from GIS by satellite imagery forms of that we can extract the data. And then if it is true,
Godwin,
satellite,
you're breaking up. Godwin?
Imagery.
I think it's
Then
better if he,
Yeah,
if he writes the
kind of
question.
yeah, definitely.
that
Godwin,
this
could you please type your question in the chat, because we're having a hard time, it's breaking up, and we'll make sure to answer it. If you could type your question in the chat, because we're having a difficulty understanding it. Did you get the question to you, Dr. Ragab?
I did hear.
Yeah, I think he was asking why was the effect of climate change more than the land cover.
Yeah. Well, this is very much specific to a catchment. And in that particular catchment, we have grassland, and what we did is replace the grassland with broadleaf trees as a scenario. And what happened is that the trees, of course, they have a deeper roots, and they take up a lot of water from the soil. And by this, the recharge gets less and less. But evaluating how much is the change in the recharge and the river flow by replacing certain percentage of the land by broad leaves instead of grass, it did not really bring severe reduction as the reduction in the rainfall. So this is really related to the direct impact of the rainfall, because rainfall has a direct impact while the land use has indirect impact on the river flows and the recharge. So that's the difference.
Thank you, Dr. Ragab. Thank you for that. I think we'll move to the next speakers. We're running a little bit late on time, but we're monitoring the Q&A and the chat. So if you could please keep writing your questions in the Q&A and chat, and we'll give you at the end another chance for another round of questions. Next, I'll move to Dr. Abdelkader Al-Arabi. Dr. Abdelkader Al-Arabi is Director of the Regional Water Center of Maghreb and Head of the Laboratory Lyman Water Resources and Information Technology, École Mohammedia d'Ingénieurs and the Université Mohammed V of Rabat, Morocco. And he will be presenting on the impacts of climate change on the Beni Amir Aquifer in Morocco. Dr. Abdelkader.
Yes, thank you very much, Dr. Ziad. So hello, everybody. So today I would like to make a presentation on some results that we did with collaboration of the ESCWA and also some organization here in Morocco. And it is relevant to the impact of climate change on the Beni Amir Aquifer, Terla, Morocco. Are you hearing me very well?
Yes, it's fine. If you could just maximize your presentation.
All right.
If you could put it in presentation mode.
Okay.
Yes, go ahead, please.
Okay, thank you. So, so what I am going to present is the results of this kind of collaboration between the ESCWA and also with Morocco, and it is relevant to the impact of this climate change on groundwater, and specifically in the Amir Aquifer, which is located in the center of Morocco. So I am going to address the key issue or problems and objectives, and I will just summarize the integrated methodology and the main steps, and also I will directly go to the developed geodatabase and the models that we have also developed for getting these results, and we will analyze the result, and at the end I will go directly to the conclusions. So Marlene, my colleague, and also Dr. Ragab already said some kind of results about this climate change effect on the world, and specifically, for instance, on UK and also in the Arab region. And Marlene has given really a lot of insight about this climate change on temperature and precipitation for Africa and also for other neighboring regions. And as you can see, the results that I have seen, it is relevant only to the impact of the quantity, but we don't have to forget the quality, which is very important, as I will say during this presentation. So that's why we need a clear understanding for the risk and the impact to inform the policy formulation and decision-making in support of effort to achieve sustainable development in a changing climate context. So here we are using RICCAR data that we got from ESCWA, and we will like to thank them very well in order to develop this modeling tools, and it is applied to the Beni Amir agriculture area. Of course, the implication will have some impacts and will pose some socio-economical vulnerability, for instance, in Morocco. And at the end, we will propose some recommendation to enhance climate resilience in light of the technical finding, of course. And this, of course, will contribute to the enhanced regional understanding of climate resilience in this area, and probably we can make some to generalize the result for the Africa or the Arab region. So this the approach is based, of course, on simulating climate change scenarios using various integrated modeling and assessment tools, and it includes, of course, the climate modeling. And Dr. Ragab and also Dr. Marlene has given more details about this climate modeling. We are relevant, especially to the key parameters like temperature, precipitation, discharge, runoff, and so on. And this should be coupled to the regional hydrological modeling. This can include watersheds or groundwater aquifers, using, of course, the output of the RCM or CGC, but it is preferable the RRCCM models. And at the end, we can have, of course, the assessment of the vulnerability for the region which is under study, and we can really get some identification of hotspots, and we can, for instance, try to see how we can make adaptation to this climate change. So I want to also highlight this problem of uncertainty, and I thank very well Dr. Ragab and also Dr. Marlene, which gave too much time to explain about these uncertainties, because it is very important when we are getting some results when using, for instance, this output of climate models and adding them to the hydrological models. Of course, we will have a lot of problems in uncertainties, and especially I would like to highlight it very, very, very well is the scales that we are using, because the scale that we are using for the models are very, very fine than the scales that climate models are giving. And this is it's really a problem that we have to solve it in the future by, for instance, refining more and more the resolution of the climate models. So that's why we have, I will just summarize, uncertainties coming from, of course, the climate models, the other uncertainties coming, of course, from the hydrological and hydrogeological models, and other uncertainties which are not to neglect, that comes from the vulnerabilities, for instance, population, agriculture, industry that we are including in the vulnerability of the climate change. So here we have some cascade of the uncertainties that you can see, and if we need really to analyze the result very, very well, we have to give more insight to this kind of uncertainties that are coming from different, of course, different steps of models. So here just synthetic diagram of how we are, of course, coupling the climate models to the hydrological model in order to get the result. I am not going to give more details on this, but what I can say is that the output parameters are used to establish the water balance, which is very important and on which all the decision makers are making their decision. So the manager will then have key elements such as the projected contribution for future years to dam reservoirs and the volumes of water renewable or mobilized in the aquifer system. And this information are of great importance for planning, management, and exploitation of water resources at the hydraulic basin scale, for instance, especially by supporting them in terms of water demand and conflict of use. So for groundwater, of course, climate change will have some effects, especially we have, for instance, the evapotranspiration, we have highly influenced by temperature when temperature is increasing, and which is the results of the climate models for temperature, especially in our region. Of course, the natural recharge also will have some impacts on the groundwater aquifers, because the net precipitation will increase or will decrease, but in our region it will decrease, and it will have some negative impact on the groundwater recharge. And we can have them also from irrigation, that means from surface water that come from, for instance, from dam reservoirs, and it will go for irrigation, and from irrigation, the water will percolate to the groundwater aquifer. And as I said before, the impact of climate change on water resource does not only affect the quantitative aspect, but also the qualitative aspect. And we are now working on some projects in order to assess the quality of water resources due to climate change. And this is very, very important, because we can have quantity, but this quantity, of course, will change because the ecosystem will change, a lot of things will change. And this is very, very, very important for analyzing the impact of climate change in the future. So here for Morocco, as I told you, so you can see already that we have negative impact of climate change, and we are, since surface water is decreasing because of the precipitation, we are now making over exploitation of groundwater, and you can see already that some aquifers in Morocco are overexploited 250% and more than 100%. All the aquifers here in Morocco because of this climate change and because of the availability of surface water. So this is just the results of the overexploitation of the aquifers in Morocco. I will go directly to the case study that we have done using the RICCAR data. Is the area, of course, it is located in the Omar Basin between the high Central Atlas and the south of the Phosphate Highlands in the north of Morocco. And it covers an important agricultural area, which is estimated to 10,000 square kilometers, and produce beet cultures to supply 3 important sugar industrial units in Morocco. So the main supplier of water resources it is the main supplier of the water resources for drinking water of several urban centers of the area, and the industrial water supply of the OCP installation and the process of phosphate washing, beside the water requirement of the agriculture of large irrigated perimeter of the Terla. So
Dr. Abdul Qadir. Dr. Abdul Qadir. We've lost your connection. Dr. Abdul Qadir? We seem to have an issue with Dr. Abdul Qadir's connection. Okay, we have an issue with Dr. Abdul Qadir's connection. Dr. Maath, you're with us?
Yes.
Okay, so maybe we can, until Dr. Abdul Qadir gets back, let me introduce you. Dr. Maath Abu Sada is General Director of Hydroengineering Consultancy in Ramallah, Palestine. And he's going to talk about the impacts of climate change on the Eocene aquifer in Palestine. Another case study using the RICCAR climate change data. Dr. Maath, please go ahead.
Okay, just 1 minute to share the screen.
Sorry to spring this up on you.
No problem.
Okay.
Did you see my presentation right now?
Yes, if you could go into presentation mode.
Yeah. Okay. Good afternoon, good morning. I don't know exactly what's the time for all the participants, but in general, I will present something about applied case study in the impact of climate change on aquifer in Palestine, called Eastern Aquifer Basin. I will go through modeling part and then the impact of climate change on this model. I think because this is the main purpose of my presentation, because the other presenters give more details about the climate change models, about modeling. Then I will go direct to the case study. Our study will be talking about one of the smallest groundwater aquifer in Palestine, located in the north of the West Bank. This aquifer is highly populated with more than 250,000 inhabitants living in more than 57 communities. Actually, most of those people depend on agriculture mainly. Agriculture represents one of the main socioeconomic sources or development in the area. Due to the lack of water or shortage of water, none all of irrigable areas are now irrigated due to the shortage of water. The main point here that the groundwater or this aquifer is the main source of irrigation. It means that you have more agricultural areas, you have at least more than the supply, and then people, they used to farming, to have plantation and agricultural practices, and water is the main constraint for expanding agriculture. This gives you impression that this aquifer located under pressure, and climate change will add more on this ecosystem or in this area. To give also introduction about the aquifer itself, the aquifer is, the rainfall is completely different from place to place. It starts with more than 650 millimeter per year as an average annual rainfall in the southwest, and down to less than 300 millimeter per year into the northeast. It means that rainfall is different from place to place. In Palestine, rainfall normally, we have winter season starting from November mainly to March. We have some rainfall in September, October, April, May, but the main months of rainfall starting from November to April. Most of the rain located actually, or the highest monthly rain in January. This is in average. And if you look to the table, you can see that the rainfall is different from year to year. In some years we have low, in some years we have very wet years. And if you go deep into daily or hourly distribution, also you will find a lot of random behavior of rainfall in the area, which impact for sure the recharge or replenishment of the aquifer system. In terms of topography, here I want to focus about, as normal, we have some mountains, we have some flat areas, but in this aquifer, you can see this green areas. We have areas with mountains with more than 700 meters above sea level, but we have at least around 7 clusters of flat areas, and those areas, they are used especially for agriculture. It means that we have very good areas for agriculture, fertilized area soil for agriculture, and this could be irrigated if we have water, and we'll have a more social development in the area. In terms of land use, this map showing the land use of the area, and in land use, more than 50% are classified as agriculture areas, or we can say that they are irrigable areas or potential area for irrigation. Of course, the aquifer is extended outside the West Bank, and this part, around 15%, is used normally for agriculture. I think this is one of the main tool or main slide representing the estimation of recharge, which is the main inflow to the system. In general, in this aquifer, the main water or replenishment or recharge is the from rainfall. And in rainfall, we have, based on different studies, previous studies in the area, we discovered that rainfall or recharge is function not of the annual rainfall, it's function of many parameters like the annual rainfall, the quantity, number of storms, number of extreme events, the duration, and all these aspects. This give you that the distribution of rainfall is very important to study the climate change. It means that if we have reduction in rainfall, then recharge could be more or less based, depends on the distribution of this rainfall. We are lucky in this area. We have more than one rainfall station. It's actual reading the data in the area, the rainfall in daily basis. And we use it normally to calculate the recharge. There are different methods or approaches to estimate recharge, which relate to annual rainfall, but the latest one or the most accurate one is calculating the recharge based on the normal distribution of the rainfall. This means that if we have rainfall well distributed in terms of monthly and in terms of daily, then we will have the highest rainfall, highest recharge. If we have rainfall season with discontinuity or less or more dry periods and so on, then we have less recharge. To know how we calculate or to define the year it's normal or not normal, or what's the linearity of this rainfall, we consider the function of linearity or normality value in Excel to calculate the normality of each season, and then we will use this normality index in order to calculate the runoff coefficients based on the previous studies. This equation at the end of our slide representing the way how we calculate the recharge. Now, before this assignment or using the model for climate change analysis or studies, we developed the climate change, the groundwater model for a period for 10 years, almost 10 years, in order to calculate the recharge for this from 2009 to 2019, in order to calculate the recharge. And I can give you a different or some results from this study. The first one, that the recharge is different from year to year. In some years we have high rainfall, then high recharge. In some years we have less recharge. And if you go, you can see the trend from 2010 till 2018. You can see there's a reduction or very clear reduction in recharge, depends on the rainfall. But in the last year, in 2019, we have very wet year, and then we have the water level again improved, and you will see this in the water level. It means that it's normally the water level or the rainfall in our area is like cycle. Some years we have high rainfall, and some years we have less rainfall. And if you compare, for example, the two seasons, 2013, 2014 with season 2018-19, we have the highest rainfall, then you can see the distribution of the recharge in this area, of the rainfall in the area of this area, which gives recharge quantities. For example, if you look to the season 2013-14, which has the least recharge event, you can see the rainfall. We have very little rainfall in October. We don't have any rainfall in November. Then we have good rainfall in December. Then you have 2 months of dry months. Then we get the lowest recharge value in the season. While in the season 2018-19, we have normal rainfall, or the best way of best distribution in rainfall. And then you can see that we have continuous rainfall. Every month we have rainfall, and at least we have 3 consecutive months or 4 consecutive months with good rainfall amounts, which creates more recharge. Then if we compare the values, then the minimum was 228 million, while in the highest year we have 138 million as recharge. It depends. It means that recharge from year to year is completely different based on the rainfall distribution. In average, we have around 76 million cubic meter per year. This is based on the actual data, measured data in our area. Now, the outflows, actually, this is one of the let's say the big problem in the area. We don't have the pumping is not well managed. It means that each farmer can drill well in his farm, or more than well in his farm, and then start to pump based on the depth of water of his well, based on his demand, based on the availability of water or the aquifer properties. We don't have any real, let's say, database about the pumping, but based on the agriculture areas, the areas irrigated, the area of irrigated lands, and the crop requirement, we managed to estimate the pumping from this aquifer, and we found that the pumping is around between 35 to 40 million cubic meter per year. This is the average pumping during the model period, and this was used in our model. Now for modeling, this is the model, the base model, which was used in the evaluation. We have this model. You can see this yellow dots representing the groundwater wells in the agriculture areas. In other areas, we don't have wells because they are mostly mountains and no wells in these areas. We have called drain boundary. It means that the flow could be exit our system to the neighboring watershed, neighboring aquifers. And we have also the constant or general head boundary. It means that a flow could be enter or leave our basin. In other areas, we have no flow boundary. This is the conceptual model of our area. It means that this model is connected to other aquifer system, and it depends on the pumping and in the recharge quantities. A flow could be even a flow or outflow could be different from year to year based on these quantities. This shows the model calibration and the water level distribution in the area. You can see that we have a good calibrated results between the simulated and the observed based on some groundwater wells, and this model was calibrated and then validated later. This shows the water direction or flow pattern of the aquifer, and you can see that the water here or the aquifer could be is divided into 2 basins or 2 sub basins. The one in the south, and all the water generated in the mountain in the southern area goes to the east through this green area to the called Far'a catchment, and all other flow is directed to the north, out of the aquifer system to the other springs in the area. And you can see the difference between summer and winter in terms of water level fluctuation in this area. But in generally, the flow is almost the same in both seasons. The water budget, and I think this is one of the main slides to represent the flow from or outflow from the aquifer and the storage. And you can see that the recharge in general, based on actual results, around 77 million per year. We have around 37 cubic meter pumping from the aquifer as groundwater destruction, around 12 leaving the aquifer to the east, 18 leaving the aquifer to the north, and the storage during this period is around 10 million, and this 10 million actually coming from the rainfall in the last wet year. Now to the groundwater or to the climate change scenarios. What we did, we follow what Berlin was said about the horizons. We compare the reference horizon between 1995 up to 2014 based on the model data, which already calibrated, and used the two other scenarios for analysis from 2021, 2040, and 2041 to 2060. And we consider that the pumping will be stay constant after 2020 because we know that it's not possible to pump more from the aquifer. It means that we assume that all the pumping will continue the same for our entire period. We try to test if we can manage a pump more, but unfortunately this is the limit of the aquifer based on the boundary condition. I will go just through the average rainfall scenario. I will not go through all these tables and charts, but you can see that in average rainfall, comparing the three horizons, we can see that in the last horizon, 2041-2060, we have less rainfall in all areas, while in the 2021-2040, in some years we have almost more than rainfall during the reference year. But we can see in the next slides that what's the impact of this change in rainfall or annual rainfall in our system. This is the estimated recharge, which reflects actually the main, but I will skip this slide to give the summary. This slide comparing the recharge or the change in recharge with precipitation or the precipitation versus recharge. And here we have very good result or very important result that you can see, for example, in this horizon 2021-2040, that if we have the blue rainfall and the orange recharge values, we can see that there is a trend. If we have more rainfall, then we have more recharge. We can see this in 6 scenarios. But in one of the scenarios, for example, we can see that less rainfall, you have more recharge, and this depends on the rainfall or the annual or daily distribution of rainfall and the number of extremes and then so on. This means that even if we have less rainfall, maybe we have more recharge. And this is just, of course, under strict conditions. And if you can see also, if we have, for example, in this scenario, we can have less rainfall, but the recharge is not affected that much. But while here we have less rainfall, but we have the recharge was impacted more. It means that reflecting that the recharge depends on the distribution. We have the same during the last horizon 2041-2060, but we can see that in all these scenarios except one, that the recharge will be less than almost 15% of the reference period. In general, or in summary, we can say that the recharge will be less, and the change would be from 5% to around 15% less recharge than the reference period. In terms of water budget, let's start from the recharge. The average recharge during the reference year, we have much more recharge during the 3 scenarios, and this more recharge reflecting in how much water leaving the aquifer. It means that if we have more recharge, this means that the outflow from the system will be escape or will be outflow. This means that some measures or more oils or redistribution of the oils in order to capture the increase in recharge. But in general, we can understand that rainfall will impact the aquifer. Even if we have more rainfall in some period, in certain period of our area management period, then this means that the storage will not be much impacted. The outflow from the system will be impacted or increased, and this will be used like storage in the aquifer system to be used in more dry periods. In these slides, we just representing the comparison between the 6 climate change scenarios, and I think this is just give you the same ideas and the percentage of impacts on climate change, and we're talking about between 5 to 15% less recharge. Let's skip all these slides. And here also what we tried to do just to analyze the model, especially in terms of the impact at local scale. And I think we have 4 slides regarding the special impacts or the impacts from climate change on the area. In this area, which is more the first agricultural area, we can see the trend in the 6 scenarios. In all times, the water level in generally decline in these wells. In some scenarios, we already have good, even better water level with the time until 2034. Then the water like this one, then the water level will start decline. In general, the water will we have decline in water level. The same thing for other scenarios, and here we can see that the drop down in this area could reach to more than 40 meters. And the same for all here for around 20 meters in the north, and here around also 20 to even or less, but around 20. And in this case, if we have drawdown, we have 2 solutions actually. Even the well will be dry and there is no irrigation, the farmer will leave their lands, or even the farmer will drill a new well or deeper well or deepening his well in order to get more water. It means that there is like challenge or clashes between the climate change and the farmers. If you have less rainfall, then farmer will deepening their wells and try to capture the storage of the system. And you can see, imagine that how much this will reflect to the socio-economic development in the area. In conclusion, this area is highly populated, highly agricultural area. Water is the concerns, or is the more let's say all people depends on the water, and water is the main concern in the area. If we have more water, this means that we have socio-economic development in this area. Otherwise, we'll have difficult situation there. Unfortunately, we have unmanaged pumping, which increase actually the problem, and due to the scarcity of water, actually this is very difficult in our area. The most important point that the aquifer is connected with other aquifers, and in this aquifer we lose, at least not lose, but at least around 30 million leaving the aquifer to other aquifers or to other areas, and this could be also managed to increase the abstraction in this area. The storage is not impacted by the climate change or by the climate. All the time the storage plus minus based on because they are already pumping more than, or at least the yield. This no space for improving the storage of the aquifer or increasing the water level, because if we have wet year, then in the next year we have dry year, then the people will try to pump more, and this will take all the storage. In general, the rainfall changing between 88 to 113% from the reference year. In the first horizon, 2021-41, and from 41 to 60, the rainfall is less, around 87 down to 87. It means that in this scenario, all models give that the rainfall will be less in this area, and this will impact, of course, the recharge. And you can see the recharge will be reduced by around 15 to 17%. If in all cases, actually in some years we have more, but in general we have reduction of rainfall. My last point about recharge and rainfall, we don't have the linear relation. It means that the rainfall distribution, the number of rainy days, the number of extremes, duration, and all the intensity, all these impact the recharge, and this will be impact the aquifer based on the rainfall. This is what I said before. I'm not going to repeat, but you can see that my last conclusion or result that climate change is very important to be studied, to be analyzed in the area, because the impacts is very, very much impacted the people there in their daily life. And actually people, at least in the last, let's say, 5 years, start to observe the climate change in terms of number of extreme events, the shift in rainfall, the shift in season, and actually all this impacted their development in the area. This is my last slide. Thank you very much, and ready for any questions.
Thank you very much, Dr. Muath. A very interesting case study that brings down to the aquifer level the changes, the climate change, and you went through the process. I think that was very well received. We'll leave the questions at the end. Next, I'll turn to Dr. Ihab. Dr. Muath, if you could stop sharing from your side.
Yes.
Dr. Ihab Jnan.
Thank you.
Are you ready to present now, Dr. Ihab?
Yes.
Okay, so Dr. Ihab Jnad is Director of the Water Resources Department at the Arab Center for the Studies of Arid Zones and Drylands, ACSAD, and he will be sharing with us a case study on the impacts of climate change on the Dibdiba Aquifer from Iraq.
Thank you, Ziad. I'll be pleased, to present this case study, and this work was done in close cooperation with the Ministry of Water in Iraq, and this will be impact of climate change on the groundwater resource in Dibdiba Aquifer system. And the Dibdiba Aquifer is located at the central of Iraq.
Ihab,
yes.
If you could minimize the windows that are not your presentation, because they're covering the presentation.
Sorry?
There's windows on the side probably that's showing participants. If you could minimize that,
okay.
It covers your presentation.
Let me see. I'm trying to move it with.
You can close it, I think.
Sorry, but I cannot see the close.
Yeah,
a little bit better, but still. Okay. Sorry for that. Okay. So, yeah, the aquifer is at the central part of Iraq, and it is in the close to Karbala and Najaf city. The area of the aquifer is about 1,000 square kilometer, and the inflow to the aquifer came from rainfall and from lateral inflow from the western boundary, as we can see here. And the outflow, it is go to the pumping well in the aquifer, and lateral flow towards the east, toward the Euphrates River. The main activity in the aquifer is agriculture activity. It's very main agriculture area. Farmer grows vegetable like cucumber, tomato, pepper, and bean. And all crop irrigated through about 1,000 pumping well from the aquifer. And you can see here the distribution of the pumping well, very heavy distribution of well in the aquifer. And of course, first there was detailed characterization for the aquifer, and a conceptual model was developed. Then a groundwater model developed using GMS software. The boundary condition, we have in the north and south, there was no flow boundary. And we have in the eastern and western side, we have variant specified head boundary. The cell, the model was 1,000 by 1 kilometer by 1 kilometer, and the aquifer is unconfined aquifer. Of course, a calibration was done for steady state and transient state for the model using the data. observed data for water level. For climate change, we get the climate change data from the Mashriq domain, as explained, Marlene explained, is 10 kilometer resolution. So we get this for 6 different model, and this was done for 4 point. This 4 point was data, climate change data was extracted for. And this is a projected rainfall for different model. We can see, I mean, for this model that expected reduction for different model range between 3 and 15% for the first point, and the same for second point. It's up to 13% reduction in rainfall, and this point number 3 and this point number 4. So we get this for the 4 point. The critical step, I mean, we had to do, I mean, because, I mean, the question was how climate change would impact the aquifer. And we found out this will be done through 2 things. First, through the change in water level at the boundary. And second, through the change in recharge. So, and what we did to consider this climate change, first, we found a relationship between the water level and rainfall, because the water level is at the boundary, changes with rainfall. And we got a regression relationship between this water level and rainfall. And we did that for the wet months and for the dry months. Also, I mean, we found, and this is after we found the equation, we applied for the available climate change data available for rainfall until 2070. So we apply, and this graph, I mean, show, I mean, the groundwater level using this equation, using the rainfall, climate change rainfall data as input to the relationship. Also, we found regression equation between recharge and rainfall based on observed data. Then we apply this equation to project the recharge based on the change in rainfall until 2070. And what I present, this is the result of the impact of this change on the groundwater level, water level map, and the water budget. We look to the groundwater level just to show an example at 4 point. And this is a first point. And this for the 6th model, I mean. So we apply this for the 6th model. So this is for the first climate model, CMCC. And at this point, point number 1, we can see the change. And there will be a drop in groundwater level from 22 to 12, about 10 meters. And at point 2, from 17 to 4.5 meter, so 2.5 meters a drop, and this for point number 3, and this for point number 4. So we can see here, I mean, it's projected to have a drop in groundwater level, and this will be between maybe 2 meter to 10 meter, depend on the location in the aquifer. And this is the groundwater level map And for the first climate model and for different time horizon. And so this for the reference period, and this is second, and this is the third. And we can see here that with time, the water level is dropping. I mean, the more red, this means the more reduction in water level. And actually, we found some cells, especially in the south and north, to get dry. It became dry cell because the thickness of the aquifer in this area is very shallow. And this is shows the groundwater budget. Sorry. And the table show different component for recharge, lateral flow, the water going in the wells, pumping well, the lateral flow, and this is the inflow minus the outflow. And we can see that it is projected in average for this model, climate model, to have reduction about 22% in average for the whole time horizon. So this for what I present only for one climate model. This is the result for the other climate model. So the result was similar with different number depending on the rainfall data. This came from this climate model. So this is a summary of the groundwater level from the 6th model. And we can see, I mean, we'll have reduction, drop in the rainfall in this north area of the maximum drop happened in this area of the aquifer. And in the south, we have this dry cell. This is for the other two model, and this is for the. So in conclusion, and we can see, I mean, result based on all climate model show decline in groundwater over the entire period with value ranging from 14 millimeter in the north to 4 to 10 meter in the middle. And some climate model projected decrease in rainfall and ranged from 2 to 15%, and some model projected increase in rainfall up to 7%. The storage volume decreasing with time toward 2070. The relative change in storage range from 1% to 106%. The result of study show climate change will have significant impact on groundwater at the aquifer, causing reduction in groundwater storage according to considerable decline in groundwater table. Actually, I mean, this result very important because, as I mentioned, this may be this area different from Palestine aquifer because this already dry, very dry area and depend very much on rainfall. Therefore, I mean, the change in climate really will have significant impact on availability of water, and which is the main source for agriculture and for irrigation of agriculture area in the basin. Thank you very much.
Thank you, Dr. Ihab. Another interesting case and an approach also to estimating recharge and changes in groundwater levels. That's a very interesting case study from Iraq. I think Dr. Abdul Qadir is with us again. Ihab, could you stop sharing?
Oh.
If you don't mind. Dr. Abdul Qadir, you're with us again?
Yes, can you hear me?
Yes, could you share and we're really running over time. So if you could be brief and continue with your presentation where you stopped.
Can you see the presentation in full
Yes,
screen?
we do. We do.
Okay, so thank you very much. I am sorry for this problem of connection. I lost my connection. That's why I was not with you. So I will go directly to probably here. So I was in the impact of climate change on this groundwater. So what I said is that we have to give more importance also to the impact of climate change to the qualitative aspect, which is often neglected. So in Morocco, we have overexploitation of groundwater. And you can see due to climate change, we have now overexploitation. And you see for all the aquifers in Morocco, so the overexploitation is varying from 2,000 to 250% to more than 100%. And you can see already depletion of the groundwater level in Morocco. And we are losing around 862 million cubic meters of abstracted water from non-renewable groundwater. So for the area that we have studied in collaboration with the ESCWA is the Terla Aquifer, and it is located in the Omar Basin between the high central Atlas and the south and the phosphate highlands in the north. And it covers an important agricultural area of 10,000 square kilometers and produces beet culture to supply 3 important sugar industrial units in Morocco. So the main supplier, it is also the main supplier of water resources for drinking water of several urban centers of the area and the industrial water supply of the OSP installation and the processes of phosphate washing beside the water requirement of the agriculture of large irrigated perimeter of the Terla. As you can see here, this is the Beni Amir area, and the proposed is the assessment of climate change impact on groundwater resources availability and use in Morocco, specifically on groundwater abstraction from the Terla Aquifer complex system that supplies domestic water as well as large irrigation schemes in the Beni Amir agriculture area. And you see here for the area, the distribution of the agriculture development centers in this important area. So for the climate change impact, we have used the RICCAR, of course, the RICCAR data from ESCWA. As you can see here from this figure, that we have decreasing of precipitation and rising of temperature. But for both scenarios, you can see already here that we have decrease of precipitation for RCP 4.5, and in red is the evolution of precipitation for RCP 8.5, and you see that we have severe decrease of precipitation. So despite case study in Morocco, we are going to see how groundwater availability will vary under climate change, and also we can see how much we can extend irrigated area if possible, especially sector based on groundwater supply, and also what are the best management schemes of groundwater. So the analysis of the climate change in water resources in the Terla Aquifer was based on the 2 scenarios, as I said before, and which entails the drawing RICCAR region climate modeling. And also we have first developed a 3-dimensional conceptual groundwater model that was designed and simulated a comprehensive set of physical processes and was compared, calibrated, and verified with observations. Of course, the 3D model is in steady state, and which was followed also by a transient management model that includes the effect of climate change on the Terla Aquifer system using RICCARs, and the period for the prediction was 2020 to the end of the century. So, but before doing this modeling, we have developed a hydrogeological database, including RICCAR. So in this database, we have the classical data, of course, of geology, hydrogeology, but we added the RICCAR data, and the classical, of course, data was collected from different local and regional organizations here in Morocco. So we can see already here for the local data of the area for both scenarios, RCP 4.5 and RCP 8.5, and for 3 models, because we were using the RICCAR data that was generated from the resolution of 25 kilometers square. And here we see already for the 3 models that we used, we have decrease and decrease of precipitation, and also increase of temperature for all the climate data. So for the area and in terms of groundwater pumping, we see already that from in 1978, so we have only a groundwater pumping in the downstream of the area, but in 1994, so the area until now it is completely covered by groundwater pumping, and we see already that the distribution and density of pumping wells for the irrigated and drinking industrial water, for the drinking and industrial water supply, is completely covers the area. So for the results of the 3 climate model, we see already here these piezometric maps for different periods, and on the left, and we see on the right that the evolution of the groundwater balance for both scenarios, RCP 4.5, which gives a scenario which is not really severe, but for RCP 8.5, we see that the groundwater balance is a really severe, and we can see for the 3 models that we have bad results concerning, for instance, the evolution of groundwater balance, while for the groundwater level, we have already a decrease for the 3 climate models, and we see that we have a severe depletion of the groundwater for RCP 8.5. For the average result, we have also generated several maps for different periods from 2022 until the end of the century, and we see here the comparison between the 2 scenarios, and we see that we have all the time drop of the groundwater table in the area, and especially for the severe scenario RCP 8.5. So for the average of the 3 climate model, we see already here the results for the all the piezometers that are covering the area, and we see here the drop of groundwater table, especially for RCP 8.5, while in the center or the upstream or downstream, we have all the time this drop of the groundwater table for both scenarios. And in terms of groundwater balance, we see already here that for RCP 4.5, the groundwater balance is varying between 200 million cubic meter to 140 million cubic meter, which is reached in 2050 in the mid-century. So we can see already here from the figure that the groundwater balance, we have a severe situation between 2020 and 2050, while after this period, we will have some improvement of the groundwater balance for the area until the end of the century. While if we analyze the results of RCP 8.5, we see already that we can get a minimum of 120 million cubic meter in 2085. That means in the end of the century almost. And this results is something less than 50% of the balance obtained by RCP 4.5 scenario. And we can see already here that this is the minimum. And we see that we have a severe situation. You can see it, and the situation will become severe from 2070 until the end of the century, because we have a decrease, a severe decrease of the groundwater balance during this period. In terms of the dryness of the aquifers, we can, from the analysis of the result, we can see already that the first layer of the aquifer will be completely dry for both scenarios, while for the second layer, we will have, if you like, a partial dryness for RCP 8.5 scenario. So we will have something around 68.5 square kilometers will be dry, and we cannot get, if you like, groundwater from the second layer. For the third layer, which is the basement, we will have something around 4.5 square kilometers that will be dry. And for RCP 4.5, so the third layer will cover something 16.5 square kilometers, which will be dry, and only 1 square kilometers of the third layer, which will be dry. So you will see already here that all this part will be completely abundant because of the availability of groundwater, while for RCP 4.5, we will have only a small part when compared to the RCP 8.5. So as a recommendation, as a conclusion, we can say that the groundwater resources in this important aquifer will be affected by climate change due to a reduction in natural discharge, of course, from reduced precipitation. And the mean of decrease will be 20% for RCP 4.5 and 50% less for RCP 8.5. So, of course, there will be also increase in the evapotranspiration, which is caused in part by higher temperature. And the mean will be 2 degrees increase for RCP 4.5 and more than 4 degrees increase of RCP 8.5 at the end of the century. For the water availability in the aquifer, it will decrease for both scenarios and will show a severe situation for RCP 8.5 because we will have a decrease of 25 meters as drawdown, while for RCP 4.5, a decrease of the drawdown will be 10 meters. So we can say as a conclusion that these results are of great importance as a key information for decision makers regarding the future of the sustainable exploitation of groundwater resources in this aquifer. Hence, the result of RCP 8.5 scenario present a great concern for the future of irrigation agriculture in the study area, since some farms will be completely abandoned due to the availability of groundwater. On the other hand, the result of RCP 4.5 scenario are less severe, but will require rational and economical management of water resources. So for the recommendation, as a key recommendation, we can say that adaptation measures that account for this impact of climate change on groundwater resources specifically in improving productivity in the agriculture sector, which are urgently needed, such as extensive reconversion of gravity irrigation to drip irrigation and adapted crops that are water efficient and more resilient to climate change. Another recommendation, which is also very important, is to assess the impact of climate change on groundwater aquifer, which must be generalized in order to underline the consequences for the entire region and seek cooperation measures for the adaptation and management of groundwater system in the adaptive and optimal manner for the studied aquifer. So at the end, I would like to thank the UN ESCWA for their kind collaboration, and also the OCP here in Morocco, also for the fund we get also, and the École Mohammedia d'Ingénieurs where I am working. So thank you very much, and I am available for your questions.
Thank you, Dr. Abdul Qadir. And sorry, we had to cut that in half on 2 pieces, but I think the presentation was clear, and I think the methodology followed was also clear and showing the effects of climate change on groundwater, which are complex and not always straightforward to predict. We have some questions in the chat. Let me just read one of them to Dr. Mu'ath. It's saying, I noticed that wastewater is dumped into wadis and it's part of recharge. Is it treated? If not, does it affect the groundwater quality?
Actually, yes. Yes, actually, unfortunately, it's not treated. And for sure, it may impact the aquifer. Unfortunately, this is the situation right now. But if you go back to the slides, then the recharge in terms of quantities, they are very minor, it's not considered, but for sure, the source of pollution. And this is one of my recommendations actually in the report to be studied very well. Yeah.
Thank you. Dr. Ihab, there's a question for you. It says, they're thanking you for the informative presentation. And the question is, I'm wondering what measures can be done, sorry, in order to tackle the impact of climate change in your study area?
Yeah, thank you. This is very important question. And we are working on this at ACSAD, I mean, as ACSAD for a long time. I mean, how to adapt to climate change. And actually, we are applying different measures in different Arab countries, in Syria, Iraq. And the number one, I mean, to work on rainwater harvesting system. And so we can store the water during the rainy season. So to reduce the reliance on the groundwater. So to use surface water from rainwater harvesting, and we apply different technique for this, like hill reservoir or Hafir to collect water, and it's proved to be very successful measures. The second measure we can do, we can apply what we call conservative agriculture. And we have very great experience at ACSAD. I mean, we did this in different countries, Syria, Tunisia, Sudan. Using this method, we reduce the needed irrigation water and even the energy and the seed, and we increase the productivity. The third measure, I mean, and we, for a long time at ACSAD, we work on developing a new variety for wheat and barley, which is drought resistance and need less water. I mean, but here we are talking on groundwater. And I guess it's very important, I mean, when we have this groundwater model, we should get the maximum benefit from the groundwater model to use it for management, to have balance between recharge and inflow and outflow. So we should define what we call the safe yield. The safe yield, which will not result in reduction or huge reduction in groundwater. So three things, I mean, water harvesting, conservative agriculture, using new variety, and groundwater management. I mean, using the mathematical model already developed. Thank you, Zee.
Thank you, Dr. Ihab. I'm just looking if there's any other questions or hands raised. Okay, there's a question that says, other than field observation, pumping tests to know the effect of one borehole or well on other wells in an area. I wanted to ask, are there models to simulate which well or borehole belong to an aquifer? Anyone would like to answer that?
Yeah, I guess this is, I don't know, this is simple question, I mean, because for you can define, and especially now with the new version of GMS, we can define, I mean, the influence area for every well. From knowing this area, we can know, I mean, for which aquifer is belong.
I don't see any other questions in this, so I would like to thank all of our presenters for an excellent presentation, an excellent useful topic covering climate change on groundwater and on surface water impacts of climate change. And also I would like to thank the attendees, although we went almost more than half an hour over time, but we still have most of the attendees with us, showing that this is an interesting topic. At the end, again, another thanks to our partners, ICID and ACSAD, and all of the experts with us today for their time and continued cooperation on this. And I'll turn it over to Dr. Muhammad. Dr. Muhammad, just a question. There was a question if you're giving out a certificate of attendance. And I'll turn it over to you and thank everyone for their participation.
Thank you very much, Dr. Ziad. And I would like to thank very much our great expert, the presenter. We enjoyed too much your excellent presentations, and it is clear for all of us the effect of climate change is clear for all on surface water and the groundwater. And we have enjoyed the case study from UK, from Africa, Arab countries, Morocco, Palestine, Iraq, and it is clear we must be ready to face the future. As it is projected, there will be a gap in between supply and the demand, and also we have significant effect on groundwater and surface water, and we must be ready how we can adapt, how we can manage our all available resources in a manner in a manner ways, and not only the effect will be for quantity but for the quality also, because it is clear when we have severe droughts, and of course in arid and semi-arid condition, it will affect the quality of available resources. So we must be proactive, and at the same time, as it is mentioned, if there is no control for groundwater, which means that the situation will be more worse, and we must be ready to face the worst scenarios. And as I mentioned, we consider all the resources, even for all conventional and non-conventional water resources, soils, crops, weather, even for the infrastructure, irrigation, and the drainage networks. We must manage all these resources in a best way, and we must be ready for extreme event. And this is what I have. Before also, I would like to thank our great partners, ESCWA, ACSAD, and all ICID, and all our partners. And of course, Dr. Ziad, for the certificates, we will prepare certificates based on the list of attendance with pleasure. And also, it will be nice to share the link for the video and the presentation also to all the attendants, and also to all our networks. So thank you very much.
Thank you. We will definitely share the link to the video, but I think Dr. Ragab has his hand up and wanted to say something. Dr. Ragab?
I would like to thank you first for organizing such really interesting seminar. But I would like to add that there is a COP27 coming up, and the Arab Water Council sent me personally invitation for side event, and it is called pre-COP27, and it will be in Cairo, I think, mid-September, just before the Sharm el-Sheikh main COP27. So I just wonder if we as organizations organize that event of today will think about contributing to the pre-COP organized by the Arab Water Council. So it's just a way maybe to continue our cooperation, and that will be the next activity between us as different organizations. So it's just a suggestion to take forward. Thank you very much once again for such interesting day. It was very useful information, and I myself learned a lot also about really what's happening in the Arab region in Africa and other places. Thank you very much for organizing such interesting event. Thank you.
Thank you, Dr. Ragab, for that. And again, we're always interested in collaborating and continuing this collaboration, whether is it through the COP or through other activities. We can discuss that, I guess, and hopefully reach an agreement on that. Again, thank you to all. I won't stay longer, but I think most of the experts are open to questions. So if there's further questions, you can send them by email, either to ESCWA or to Dr. Muhammad, and we'll be happy to answer these questions and go into further details with you on this. So again, thank you all and hope to see you soon. Bye-bye.
Bye-bye.
Thank you, Ziad.
Thank you. Bye-bye.
Bye.
Bye-bye. Thank you.